Afternoon, everyone. It is now a minute past the hour, which is our usual starting time. I noticed a few folks have signed in the last minute. In any case, my name's Roger. I will be doing my best to bring you up to speed, so to speak, on what's going on with electric vehicle charging, and assuming that probably almost everybody in the group is going to get involved one way or another, either for yourself or somebody else or through your company or whatever. A couple of basic practices here. What we like to do with the large group, we've got 43 people now. So it's really not practical to have open microphone day. So if everyone will remain muted, and if you have a question, type it into the Q&A. All right, type it into Q&A, and we'll reserve the chat for communication with the host. If there are any technical issues, let him know, and he'll be adding things from time to time about where do you get copies of the slides and what about certificates, all those kind of administrative details. So go to chat box for talking with the administrator, and Q&A if you want to discuss the presentation. And with that, off we go. Normally, I'd say let's just let everybody introduce themselves, but that would take half of the time we have available with 43 participants. So what I want to do is try to dispel some of the myths that are going around with, I think almost everything is something new and useful and whatever. Somebody's always going to spread rumors that they're bad. And so we want to get rid of any of those rumors, get the right answers, and make sure. And one of the more interesting things is, residential charging is relatively straightforward, but we're going to talk about checking on whether the service size is big enough, depending on charger size and so forth. So let's get started. You notice the way the times changed there. They changed a lot faster toward the end, which is exactly how it's happening right now. Probably whatever you hear in the webinar today will be super. Somebody tomorrow will come up with something different. But what I want to make sure is everybody understands the basics here. Like, how many miles does a electric vehicle get to a kilowatt hour? How long does it take to charge with the 9.6 kilowatt level 2 charger? And how many of those can you have on a single circuit, and on and on. So that's what we want to get down to. It's the nuts and bolts here of let's make sure that when somebody comes at you with some strange question about EV charging, that you'll be right on top of it and be able to answer them. So here we go. A little credit for some of the people, but it's pretty important to look at the forecast. If you look at what Edison Electric Institute says, they say that, okay, it's 2023, 4 million of these electric vehicles on the road, but by 2030, we're going to see about 18 and a half, almost 19 million here in the United States. And that was projected back in 2018. So, and we seem to be right on track for doing that. And I know when I look around, it seems like every day there's a few more Teslas out there, and every once in a while you even see a hot electric Mustang and stuff like that. So here's what we're looking at, and that means that's a lot of extra work for somebody. They're all going to have to be charged one way or another, and a lot of them will be charged in somebody's garage on a simple level 1 charger on a 20 amp circuit overnight, 10 hours if necessary. Get that extra 50 miles of driving. And that's good enough for most of them. And we're going to look at as many different variations on that theme as we possibly can. Probably single family detached is the easiest. Generally, the charger comes with the vehicle. It's level 1 that can be plugged into a 20 amp circuit, and you're done, because it's probably a 20 amp circuit in your garage that you rarely use. However, not everybody has that possibility, so there will be some cases where people are either going to want a level 2 charger and may not know whether that's going to fit or not without a service change. So we're going to look into what you need to figure out in order to make sure it's going to go without shutting down the main breaker. I'm guessing, since this is what I'm seeing, is that there are parking areas that have chargers in them. And pretty soon, it's not going to be practical to have a motel unless you've got EV chargers available that will charge up the car with 200 miles or so overnight, and maybe even more. And it may well be that those rooms will be rented out a whole lot faster. So I think we could look forward to a lot of EV chargers being installed in motels. So we want to talk about what are the constraints and how do we deal with that? And this is my fun one, because condo next door to me where I live, they have a policy that if you plug in an electric vehicle into any of their outlets, you are fined $250 because you might burn down the building or whatever. So that's the kind of resistance that's being seen in some places. But that is not stopping people from buying electric vehicles, because once you get a ride or once you drive it, you want one. We've had a plug-in hybrid since 2018, and it's the finest automobile we've ever had. And we've ridden in some of the other straight EVs, and they're fine automobiles as well. And very inexpensive to operate once they're in your garage. So anyway, here's the numbers. Let's look at the two types. There's all electric, okay. Has a range somewhere between about 100 and 400 miles, and battery capacity between 30 and 100 kilowatt hours, more or less. Like I say, all this stuff is changing by the day. Tomorrow might be 102 kilowatt hours, who knows? Most of the batteries are lithium based. Most of them are LFP, lithium iron phosphate. But there are some other lithium technologies that are also being used and catching on. And there will be some other really fancy high mileage solid electrolyte type batteries coming up here another few years. So very interesting stuff is going to be coming up. In any case, this is what we're looking at for the all electrics. The plug-in hybrids simply have a smaller battery pack, and or it's a hybrid vehicle with a larger battery pack that can store some extra energy if you plug it in overnight or for a couple hours. These vehicles have about 350 miles on gas and 50 miles on electric, typically, with about a 17, 18 kilowatt hour battery pack. So we want to talk about charging times and all kinds of numbers here today, and I hope that you'll take some home. I encourage you to order up a set of the slides. They're my copyright. The reason I wrote them is so people will have a chance to have them, read them, share them, and help dispel the mythology out there. And hopefully that will be good for everybody. Okay, so electric only, maybe drive about 50 miles. And then you, I mean, on the plug-in hybrid. And if you have to go more than 50 miles, you either stop to charge or you use some gasoline. Okay, what about charging these things? Well, NEC 625 is the National Electric Code reference for charging, and they recognize certain vehicles as electric vehicles: passenger automobiles, buses, trucks, vans, neighborhood electric vehicles, electric motorcycles, electric golf carts, and forklifts. They're not intended for use on the road, so they don't count. And you notice I don't have electric bicycles on here. On the other hand, they would probably be classified as equivalent to an electric motorcycle. But then what about electric scooters that you just ride along the sidewalk? They're not exactly intended as highway vehicles, but you certainly see a lot of electric bicycles on the road. So I'm guessing that I haven't looked at the 2023 National Electrical Code, but it'll be hard to believe they won't add electric bicycles to this list. The requirement on EVs is they have to use the rechargeable batteries. You can't use batteries like this in an EV. It won't get you very far. And besides, you have to keep changing them because these are not rechargeable. So let's just do some numbers here on fuel costs. And we're going to start with $4 gas and 15-cent electricity here. Of course, your numbers may be different in your neighborhood, so you just put in different numbers and do the same math. Because if you've got a full-size SUV at 20 miles a gallon, 1,000 miles will use 50 gallons of gas. That's easy math. It's called long division, or maybe even with the calculator. And 50 gallons at $4 is $200, or in other words, $200 for 1,000 miles is 20 cents a mile to drive a big SUV. Okay, if we have a little cute little at 30 mile per gallon SUV, then you're looking at $133.20 for 1,000 miles worth of gas. And if you've got one of these things, a hybrid that gets 55 miles per gallon, and this is not classified as electric vehicle, but it's got some electric backup and helps a lot. You're looking at $72.80 to go 1,000 miles. And if you got either a plug-in or a standard electric operating only on electric at 4 miles per kilowatt hour, which is what most of them are advertised to give you. If you look on their specs on the internet, they'll show 100 kilowatt hours gives you 400 miles, give or take. And that doesn't count if you run the air conditioning and a lot of other stuff. You might drop down to 3.5 miles per kilowatt hour. So a nice conservative number is 3.5, but 4 miles works for rough estimates. And if you get 4 miles per gallon, that's 250 kilowatt hours for 1,000 miles. At 15 cents, that's $37.50, which is half the cost of a hybrid at 55. So that means you're looking at roughly the equivalent of 100 miles a gallon with electric only. And we'll look at, oh yes, that electricity, there's carbon generated in the process, and we'll look at that in a minute. In the plug-in hybrid, if you go half and half, 500 on gas and half on electric, it's going to use about $40 worth of gasoline and $18.75 of electric for $58.75. So if you use gas in that plug-in hybrid, it's looking at somewhere 40, 45 miles a gallon, maybe a little more. And that adds to your cost of operation. But anyway, this is a rough estimate, and you can do the math for your neighborhood using whatever your electric and gas prices are. Comparison on carbon dioxide, electric versus gasoline. By the way, I wanted to mention that we've got some work going on in the building here with jackhammers, and in the past it has not interfered. The noise filters on the webinar program seem to work fairly well to filter out jackhammers, but if anybody hears any, I would like to see a hand up or something that you do hear some background noise, because the intent is to not have that, or at least mostly you need to be able to hear and see the webinar. There may be an occasional interruption from a jackhammer. We live in Florida where that building collapsed, and now every building along the coast of Florida has to have their 100 or 40-year inspection and fixing. We started 5 years ago. We're still working on it. So hopefully we'll be done another 6 months or so. Okay, let's look at some CO2 comparisons. Here's an EV at 10,000 miles on renewable electricity. What does it do? Well, no CO2 release, about 15 cents for electricity, maybe. Turns out that in my building, a condo, we're on a demand rate here. So our kilowatt hours are only 8 cents, but then there's a demand of about $11 to $12 a kilowatt for demand. And if you eat into that, that could add to your cost. But if you charge at night beyond peak, the cost of the electricity is around 8 cents here. And it may be different where you are, and you may need to use different numbers to do this same analysis. But in any case, 10,000 miles on renewable, we're using a more conservative now, 3,000 kilowatt hours. but still, that's about $450 worth of electricity, or $45 per 1,000 miles. No emissions, no carbon monoxide, no nitrogen, no anything like that. And furthermore, the electric vehicle batteries are available if the vehicle is so equipped to sell electricity back to the to the utility as long as it's plugged in. So at a negotiated price with the utility. So that's an interesting situation. If we look at a gasoline vehicle, 10,000 miles, 25 miles per gallon, what the numbers are? Well, first of all, it's 400 gallons of gasoline. So that's $1,600 worth of fuel, ever so slightly more than 450. Then we look at 7,840 pounds of CO2 released versus zero. That's a little bit more. And of course, I say zero, and we're going to look at how much CO2 is involved in the production of electricity too. So nobody can go off saying, "Oh no, but he just used something that's not real." We're going to get real in this thing. Don't worry about that. If we convert 7,840 pounds of metric tons, which is the way a lot of other people like to count weight, that's 3.56 of them. And given that there's about 275 million cars on the road averaging 25 miles per gallon, that adds up to a mere 2.16 trillion pounds of CO2 a year. So the major contributor to carbon dioxide in the atmosphere is vehicles burning petroleum. And if we look at electrical generation, the average CO2 per kilowatt hour is about 0.92 pounds per kilowatt hour. That's the United States Energy Information Administration came out with those numbers in 2019. It's probably ever so slightly better than that now because the utilities are moving from coal, which is about 2.2 pounds per kilowatt hour, down to natural gas and a lot of renewables. The natural gas is somewhere in the neighborhood of 0.9 pounds per kilowatt hour. So if we have less than 1 pound per kilowatt hour, and if we're getting 4 miles per kilowatt hour, then we're looking at about 1/4 pound per mile. And in 20 miles, that means 2.5, 5 pounds instead of 20 pounds. So we're still down by 75% using utility electricity generated that uses some natural gas in the mix. And there's very little coal in the utility mix now. It's mostly natural gas. I'm going to look at the chat and make sure those are all chats and that none of those belong in the Q&A. So give me just a minute and see what we got. How can you download the slides? Okay, that's all answered already. Starting at 2:02. Please go ahead. Can't access the handouts. That's the administrative. I'm sure that's been solved now. Okay, good to go. Those are all administrative questions. Okay, so it looks like there's certain advantages to having electric vehicles, both from an energy standpoint, from a maintenance standpoint, from a pollution standpoint. There's just a lot of good vibes there involved with those things, and maybe that's why so many people are buying them. They're finally finding out the secret. So let's talk about charging levels. Level 1, simple 120 volt. Generally, the maximum is about 1,920 watts because that would be 120 volts at 16 amps, which is the maximum allowable continuous load on a 20 amp circuit. So the charging levels around 1,800, and if it works on a 15 amp circuit, then and the level chargers that come with the electric vehicles are usually level 1. All right, I see the Q&A up there now. We're going to come to that in just a minute. Okay, let's do that right now. Any pollution loading info on batteries? Well, the word on the batteries is that after 2 years of operation, they pay for any additional, or let's say the marginal cost of CO2 that an electric vehicle contributes during the manufacturing process versus a regular gasoline vehicle. So after 2 years, you're home free on that. That's the numbers I've heard recently, Mike. So hopefully hopefully that's what you were asking. I'm glad you asked it because a lot of people do ask that. Okay. So a level 1 typically charges somewhere in the 1500 to 1900 watt range and plugs in just like it shows here, but this could be plugged into a level 2 charger as well because the charging head that plugs into the car, they all look the same. So what is level 2? And we'll look at charging times here in just a minute as well. Level 2, there's a lot of different level 2s out there. They go all the way from 3,840 watts, which is 16 amps at 240 volts, and runs on 2-pole 20 amp breaker. And it goes all the way up to 19,200 watts, which uses 80 amps, which requires a 2-pole 100 amp circuit breaker. And for the moment, that's the biggest I'm aware of. They might be making some bigger ones at level 2, but we'll see what various sizes of level 2 will do in terms of charging times in just a minute. Level 3, that's the fast charger. They're in somewhere 50,000 to 350,000 watt range, and generally connected to a 3-phase service. And what that means is charging, you're looking at, say, 200 amps at 1,000 volts DC and the charging, because 3-phase charging, level 3 charging is always DC as opposed to AC. Level 1 and level 2 are AC charging. So 200 amps at 1,000 volts or 420 amps at 480 volts. So that's not a residential option. Those are going to be someplace that have a very big service coming in. Like on the freeway or on the turnpike where people need to stop for half an hour worth of charge to give them 200 miles. That's what's going on now, but it's going to be more than that in less time within another few years with improvements in battery technology. So the question is, do you wait 2 years or you just get one now and then buy another one later? So anyway, level 1, level 2 are AC. So that means the vehicle itself has to convert the AC to DC in order to charge its batteries. And if the vehicle is going to try to send some power back out to the grid upon a request by the grid, it's going to have to change it back to AC again. And most of the vehicles right now don't have the inverters to do that. But the National Electrical Code in Article 625 actually does have a provision that says that if you have an inverter for extracting AC from an electric vehicle, it has to comply with IEEE 1547-2018. So they're anticipating this, so it's coming, and probably does exist in some areas, but just not in my area right now. So there's your charging levels, 3 of them. And charging times, all right, this is really important. This is where people really get confused. If you're, right now, if we're looking at, say, an average between 3 and 4, or in other words, as I was earlier saying, 3.5 miles to the kilowatt hour, then it's a matter of how fast can you pump these kilowatt hours into the batteries. And not only that, but how far do you drive every day? In our case, our average daily driving is about 15 miles. But we don't drive much. We're old, and old people, well, that's not true. I've been passed up. Old people sometimes drive a lot faster than this old guy does. But in any case, if we look at 3.5 miles as kind of an average number for EVs, then we can come to certain conclusions. Level 1 with 1,800 watts, that's 1.8 kilowatt hours per hour, okay? And if you take that times 3.3 miles per kilowatt hour, you're looking about 6 miles an hour of charging. That's another interesting 6 miles an hour, and that applies to how fast you're going, but also how fast you're charging. So for every hour of charging at level 1, you can expect somewhere between 5 and 6 miles of additional distance added to your batteries. All right, and it doesn't make any difference whether you're an EV or a plug-in or whatever, because you talked about the electric operation of the vehicle. All right. So that's a good number to keep in mind, 6 miles an hour for level 1. All right, here's level 2 at 8,320 watts. Why 8,320? Well, if you divide 8,320 by 240, it comes out to an interesting number. 8,320 divided by 240 just happens to be 35 amps. Now, that's divided by 240, but if you divide it by 208, okay, 8,320 divided by 208, which is typical in a lot of bigger buildings, it comes out at exactly 40 amps, which means that you have to multiply that by 125% for your wire sizing and your overcurrent protection. In other words, you use a 50 amp charger on this. So a 50 amp charger in a condominium or any other building, an office building that's served by 12208 is going to run at about 8,320 watts. And what that does, of course, is increases the battery charge by 8.32 kilowatt hours per hour. And 8.32 times 3.5, we're looking at about 30 miles an hour. All right, so level 2 at 8,320 watts, roughly 30 miles an hour of charging. Charge overnight for 10 hours, 300 miles. So, you know, who drives more than that? For most cases, this is more than adequate. Simple 50 amp circuit, and maybe even a smaller circuit gets you more than you need plugging in every night at wherever you park your car. So just important numbers to realize when people ask you about, oh, well, this, you know, whatever they might say. Okay, here's the deal. 30 miles an hour for charging for level 2 at 8,320 watts. And if you have bigger, more watts than that, then you can charge at a faster rate. But this is a fairly nice intermediate measurement. And level 3, if you pump 125,000 watts, that gives you about 63 kilowatt hours in a half hour. And of course, that's 210 miles per half hour. And at that rate. And keep in mind that the chargers do not run full speed ahead for the entire charging cycle. Once they get up to about 80%, then they start slacking off. And this works whether it's your cell phone or your car or whatever. It's very interesting to just do an experiment with your cell phone. Plug the thing in, check the state of charge, mark the time, mark the state of charge, come back in a half hour, put another data point down, another half hour, put another data point. And you'll see how it goes up to about 80% at one rate, and then it's very smoothly curves over and levels off to 100%. And this is pretty much characteristic for all chargers with most batteries out there, the lithium or whatever the battery technology might be. So that's why you see that in like on the freeway, your fast charge doesn't charge you to 100%. You get up to about 80. We have a question. Let's see what we got. 15 cents for level 1. What's the cost for level 2 and 3 since the demand is higher? It's all a matter of whether you're on a demand rate. Mostly residential systems, you're not on a general service demand rate. You're just on a so much per kilowatt hour. So this 15 cents a kilowatt hour is typically what you're looking at for a residential service. And if you're in a condominium building like mine, my price per kilowatt hour is 8 cents. But then if I'm going to factor in demand, every kilowatt of demand, if in fact I happen to be charging at that one time during the month when we're at our maximum demand, that's going to cost an extra 11 bucks or so. So if you're charging during maximum demand, there are other utilities. I have to know there's some rates. If you go time of use rate up in Minnesota, that seems to be the best way to go. My grandson just got a Tesla, and he's an engineer, and he did the math, and he concluded he's going to switch over to time of use. But there are also some that will say if you charge between midnight and 6 in the morning, we'll sell you electricity for a nickel. So and forget about the demand. So it's all an individual situation. You got to talk to your power company to find out what their deal is. But anyway, that's where the demand factors in, and you know what the power rating is in level 2. So if you got an 8 kW, then that could cost $80 or so for the extra demand if you hit it right at the wrong. On the other hand, demand limiting, all these chargers have demand limiting. You can tell it that if you are pushing my demand beyond a certain level, then stop. Don't do that. Wait until demand goes down from all the other appliances and stuff. So this is something people are well aware of. The controls people are going crazy with it, doing a lot of interesting stuff. And it's certainly a matter of concern, but it's also an easy matter to solve, unless the only time you can possibly charge your car is during utility peak. Then that's when you go into solar. So hopefully that I don't want to go into too terribly much detail. Hopefully that picks up the essence anyway. Now let's see. We had we got 9 in chat. What does that mean? I hope nobody's typing in questions for me in chat. If you've typed something in chat, I'm reading the Q&A. So please shift it over to Q&A if you would. If you're asking in chat, that means you want to talk to the host about some technical issue. Okay, so what are some important observations about charging times? Well, typical electric vehicle is probably going to be driven about 10,000 miles a year. Okay, typical. No, some 20, 30 work, but then there's like ours that we drive ours 5,000. So 10 is not too unreasonable, but again, put in your own number and then do the math. If you're 10,000, then that's 27.4 miles a day. And again, that's average. So some days you do less, some more, 27.4 average. So we're dealing with averages here. And let's just say 30 miles a day. Well, what did we just learn? We learned that level 2 charger charged at 30 miles an hour. So how long does that take to charge for a day's worth of electricity for the car? That math is not too complicated. 30 by 30, let me get my calculator here. What is that anyway? That's 30 divided by 30 equals 1.0000. Looks like it takes about an hour, huh? But if you got level 1 charging at 6 miles an hour, you got 5 hours a day. Oh my goodness, do I have to wait 5 hours to charge the car? Well, how many people sleep less than 5 hours a night? Because we have a totally different algorithm now. We don't go to the gas station every Saturday or every 2 Saturdays or whatever and fill her up. We go to the electric station where the car gets plugged in every night, and we fill it up overnight in maybe 10 or 12 hours. And so 5 hours a day of charging with level 1 is, for most people, is no big deal. If it is a big deal, then you move into the next level. But that's the first experiment you do. And we've been doing that experiment now for 5 years, and we've never been disappointed. So level 2 at the 30 miles an hour rate, it's an hour a day. So what are you going to do with that charger for the other 23 hours? My goodness. Well, gee, maybe you could share it with somebody else. Ooh, my goodness. Well, we'll talk about that later. Okay, so if there's excess renewable energy available during the day, then what a fine place to store that excess renewable energy. Just dump it into your electric vehicle and then use it sometime when that renewable energy isn't there. So this is totally unheard of, that we're going to actually use renewable energy during the day when peak time. Well, it's conceivable as we move into a renewable energy economy over the next 20 years, and we're moving fast to approaching that fast. We're in double digits now, and that is double digits in percentage. And that means it doesn't necessarily take more than another 10, 20 years before we could be all electric. And if that happens, an hour a day for your car gives an hour a day for 23 more cars. So interesting. And also interesting possible use of any excess that might be in the car to store it, and even able to give some back. You got 100 kilowatt hours in your electric tank and you need 20. Why not sell 5 of them back to the utility when it needs it if you get 30 cents or 25 cents a kilowatt hour? If system's available 18 hours a day, then we can say, okay, don't load management. We're just not going to charge during peak time period. We'll set the timer on it. Well, then you can do 3.6 EVs a day at level 1, or you can do 18 a day at level 2. 18 on a single 50 amp. I see it says 40 amps here, but that's 40 amps of charging current. It needs a 50 amp breaker. So on a single 50 amp circuit, you can do 18 cars a day. No, a lot of people don't think about that. And that doesn't mean you have to be moving the car out and pulling another one in, because you can hook up 18 chargers that talk to each other on a single 50 amp circuit, and they will talk to each other and limit the amount of current they draw collectively to 40 amps. And there are a number of different algorithms they can be programmed to do that with. First in, first out, first in, or everything even for everybody, or somebody who's willing to pay more. This is going to change month by month. Creative new ideas on this. So pretty interesting stuff. So the idea is just keep these in mind when we now look at some of the design rules. Okay, here we go. I'm really curious. 9 chats. What is happening here? Oh, okay. All right. Somebody says thank you. That's okay. Oh, okay. Lots of good information. Okay. All right. That's good. So what kind of features would we like in our EV charger? Well, the basic charger should be compatible for, your car and my car and everybody else's car should be able to plug into it. Should be able to communicate. Even our simple chargers that we plug into the 20 amp circuit in the wall, when it's plugged in, it talks to my partner's cell phone, and she can just check on her cell phone to see whether it's fully charged yet or not, or get all kinds of other information. So the chargers are real helpful communication items. In fact, they even tell your car that when it's plugged in, it's not supposed to back out of the parking space, and it won't let you. And that's pretty important communication part. It'd be nice if they weren't very expensive to install. And in fact, if you get one that comes with the car that you just plug in, your installation cost already went down to 0, unless you decide to put a couple of screws in the wall to hold it there so it won't be just hanging from the socket. And it does weigh about 5 pounds, so it's kind of nice to screw it to the wall so it just doesn't have as much force pulling on the cord. And that wall outlet needs to be more than 18 inches above the floor and all those kinds of rules. But we want it to be safe, and so they're designed with all kinds of safety features, want to be code compliant. If you look at this J1772 plug here, you can see the 2 big ones on the top are the hot lines, line 1, line 2, and that could be line 1 and neutral. This thing is not fussy whether you connect it to 120, 208, or 240 across those 2 pins. The one in the bottom is your ground wire, and the 2 small ones are your communication link that tells your car that is plugged in. It also ties into your cell phone link, and it can collect data as to how much charging current have you dumped into the car and how full is it, and things like that. So that's what's right there now, and you get one of these things in the picture with your car when you buy it. A little more advanced is bidirectional. You notice that's in bigger type, because that's going to be, I predict, you can write me down as predicting by 2030, this is going to be a real big deal of being able to sell back to the utility. Yes, your batteries wear out a little bit faster. On the other hand, if you're going to dump 5 kilowatt hours a day out of a 100 kilowatt hour battery pack, that is not a huge amount of discharge. And if that will help you to pay for your battery pack, you just have to make sure you sell the electricity back at enough so that you don't lose money on the deal. And so this is going to be a big thing. And they should be adaptable, just like the others. You can plug them in wherever you need to be plugged in, portable, hopefully throw it in your trunk and take it to wherever you're going to plug in. but they are going to be very smart. And that's in terms of billing, load management, and networking. And lots of them are already very smart for all these things. So, but those are a little more advanced than the simple thing that comes in the trunk with the new car that you buy. All right, so that's what we'd like to have. So what is the typical level 1 and level 2? They look something like this. Might be at a car dealer, might be plugged in on your wall in the garage, might be out in the parking lot of a library or university. So you're plugging, charging somewhere in the 25 to 30 mile an hour range with most of these chargers that a lot of the municipalities are putting those up at public buildings like libraries, and some of the universities are putting these up in the middle of the parking lots. So you may or may not have those in your neighborhood. I'm guessing you probably do. And if you don't, maybe you'll be a part of making sure that happens. So some of these chargers can actually convert between level 1 and level 2 with an adapter. So a lot of interesting things out. We're pretty well standardized now, but there are some discussions going on about trying to standardize on the higher charge rate stuff. And my understanding is that Tesla and Ford have been having some conversations about that. Where would you put a level 3 charger? Someplace where you get a meal in a half hour. There's your half hour's worth of 200 miles extra to drive another half hour for another Big Mac and another charge. And here's a Q&A. Let's see what we got. Math indicate a level 1 charger being practical for a typical use profile. Hey, we have to define typical. And a typical use profile would be, if you're going to drive more than that, say 50 miles a day or 100 miles a day, then you're probably going to be somewhere where you're going to have to charge somewhere other than at home. And the cars themselves generate their own histograms for that matter. So you can get that. And I have not seen any compilation of there are some people who just can't stand the idea of taking 6 or 8 hours to charge their car overnight, even if they are asleep. And these are the folks who are going to put in level 2 just because they're living at a fast speed and they want their car to be just as fast as they are, instead of them to be just as fast as their car. So that's the best I can do for an answer to that question. But the math is there now, and you can do your own math to see. You could do some of your own use profiling and measure mileage, speedometer mileage at the beginning of the day and the end of the day, and do that for a month, and you probably could publish a paper on that. And then all you have to do is define yourself as average. Or you could say that's the average for you. And really, these things do kind of boil down to personal situations. And you can figure out how many miles a year most people have a pretty good idea how many miles a year they drive. So, but yeah, Michael, this is, I'm glad you point that out, because it's the sort of thing that people ask about. And it's the kind of thing that I want to make sure everybody's got some answers to those questions. So here's your fast charger. Half an hour plugged in gives you 80% of a tank of electricity and maybe a cheeseburger. I don't know what they charge for the electricity at these, and maybe they pay for it by raising the price of the cheeseburgers by a nickel or something. Just don't know. Or maybe a little more than a nickel. If you want 200 miles worth of electricity in a half hour, at 15 cents a kilowatt hour, well, I guess you're looking at something like $7.50 worth of electricity. So you're probably going to have to stick your credit card in that machine somewhere and let it bill you. But clearly, Tesla's got the market on this one, and they've got all kinds of fancy. They do a lot of thinking about how these things ought to work and how you bill and all that stuff. And this is what you're looking at. See those two big connectors? That's 100 amps. That's number 3 wire. That means a lot bigger charger. Then you got your communications and ground up in that top thing. But your big time current goes out of the bottom of this charger. And that's for DC. And here's your definitions, all of different charges. This is the combined charging system here for type 1. Okay, so what are some of the applicable codes and standards? I'm going to zip through this kind of fast because if you really want to know, you'll download a set of slides and you'll be able to look them up. But the big time things to look at are NEC 220.87 and NEC 625. And so we're going to pay a lot of attention to those in the next hour. When how much we got left here? Better check. 2:47. So we got an hour and 15, hour and 13, something left. We're going to pay a lot of attention to 220.87 and 625.41, I think it is. And then these are NEMA standards for connectors, and then we got the SAE J1772 for the thing you plug into the car itself. And these are all pretty well standardized, thank goodness. Otherwise, there'd be that nightmare that occurred before we standardized nuts and bolts into a certain number of threads per inch and diameters and stuff. Well, now you get a 1224 or an 832 any place you want to, and they're standardized. And of course, the communication ought to be standardized as well. And that's their open charge point protocol. And that is how a lot of the chargers talk to each other. And like they'll say, if you're going to have multiple chargers on a single circuit, there's going to be a current transformer at the origin of that circuit. And as soon as it reaches maximum current, that charge controller is going to send messages out to the chargers and say, okay, guys, you got to work it out here now so that this is how many amps you've got. And you're either I'm going to decide for you or you're going to decide not to overload this circuit. And it's generally a combination of the two deciding. And sometimes even the car could get involved because the car would probably be programmed to say, if the electricity is too expensive, don't buy it until the price comes down. If in fact you're plugged into a variable price source of electricity, which is probably some are going to be like that, I'm sure. So UL 2202 is a standard for EV charging systems, and you can buy one all for yourself. If you got an extra $1,000, you send it off to UL, and before you know it, there it sits either in your excuse me, either your inbox or a mailbox, snail mail. So UL 2231, standard for personnel protection systems for EV supply circuits. Well, wait a minute, what in the world, is it that bad? Well, if you're talking 1,000 amps or 1,000 volts or so, then you got to be a little careful around those, and you need some standards to make sure people don't get reckless around that kind of voltage current levels and power levels. That could be some nasty arcing. And then there's the North American Charging Standard. Tesla and Aptera are trying to put together that there's just a single connector for all levels, 1, 2, and 3, rather than the two different connectors that we've just seen. And sooner or later, that's probably going to be out there. And if you want more information, here's a reference to Google that out and keep up to date on what's going on. And if you look at it every single day, it's probably going to be different every day because it is moving fast. And if you want to know more about OCPP, you can learn from Wikipedia how it works, and helps know a little bit about that as well. But just knowing that if you've got two chargers, both of which speak OCPP, they can talk to each other and they can be controlled by another controller that limits the amount of charging they can do without overloading the circuit. 625 is really important. Here's a Q&A. Let's see what we got. No, larger scale data available for utility to determine the load profile impact for EV deployment to help determine service feeder and substation sizing. I don't know where that is because that's not been of my major concern. My guess is utilities know where to get it. because a lot of the chargers, the utilities can monitor to know whether that car, by way of that open charge point protocol. So no, what I do in my spare time is I check plans for residential photovoltaic installations, and I've discovered that at my age I just can't know everything, and so I have to just say that's a really good question. And if you can find out the answer before this webinar is over, please share it so everyone will know. But you can bet that the utilities are paying very careful attention to what their overall load profile is looking like. And they shouldn't necessarily care what's happening with PV. They certainly measure on an hour by hour basis exactly how much demand they've got. And whether it's from water heaters or whether it's from electric vehicles, the electrons all look the same. And there must be some pattern that they're using to develop exactly how much storage they themselves have to provide. Florida Power and Light, for example, has decided it'd be nice to have an extra 300 megawatt hours of storage. That they built a pretty big storage field up in northern Florida. So you got to bet that the utilities are paying a lot of attention to what's going on with EV deployment, and they're trying to shift as much charging off peak as they possibly can. And you can bet that they're hoping that the EVs will be around during peak time to be able to provide them with some peak time electricity, because some of the other sources of peak electricity are very expensive. And they would prefer not to have to use those if they can get it from a different reliable source. And with 100,000 EVs on the road at some point, there's going to be a lot of them plugged in at times when utility could use some of that electricity. So that's maybe a longer answer, but there's a lot of speculation in it. On the other hand, a lot of it makes pretty common sense, and I'm sure that we're going to see a lot of that sort of thing going on. Let's quickly run through the NEC rules, because I want to get to do some designs. And you'll be able, if you're serious about this, you can check these slides out again by just ordering a copy. Excuse me. I did a webinar this morning for 2 hours also, and see, I guess it's starting to sink in here. My throat is rebelling, but I do have water handy, so I'm going to do my best to balance that out with other needs. Okay, so 625.2 says electric vehicle storage battery does not release gas. That's really important, because if you had a lead acid battery, that gives off hydrogen, and it does not qualify as an EV storage battery because it gives off hydrogen. But the lithiums don't. They don't give anything off, but you also don't dare charge them over 100%, and they've got extremely complicated and complex battery management systems to make sure that doesn't happen, including slowing the charging rate down as it approaches 100%. But they don't just measure the voltage. They actually integrate the current coming in, and the charge is the integral of the current over time. And they do that integration on a cell-by-cell basis. And that's a goodly portion of the cost of the battery itself is the management system. Okay, fasten in place. You can move it without a tool. Fixed in place, you need to take a screwdriver to loosen those 2 screws to get it off the wall. 625.4 says that these are the nominal AC system voltages that you can use for an EV charger. You all the way up to 1,000 volts for AC, and you can also go up to 1,000 volts DC. EV supply equipment, EVSE, and wireless transfer equipment. People are designing systems where you just pull over a thing that has a higher frequency current going through the wire, that a little bit easier for transformer action. And so you have a wireless connection to charge the vehicle. Not too many of these out there, I don't think. I've never seen one. But provisions for installing and using those are in the NEC already. Part 2, manufacturing specs in order to get it listed. Of course, nobody wants to buy or install any kind of equipment unless it's got a UL listing. A little more of 625, each outlet has to be on a single branch circuit. Yes and no, there's settings that say, yes, each outlet's on a single branch circuit. On the other hand, there are provisions for sharing, but that's done by software. But the design, you design as though it's on its own branch circuit. We're coming to that. 41, this is the important one right here. Branch circuit overcurrent protection must be rated at 125% of the equipment rating. Okay, so you got a 40 amp charger, your branch circuit over protection is 125 of that at 50 amps. Okay, so the calculation, and that's your wire sizing as well, because you're assuming it's a continuous load, even though we know charging 30 miles an hour may only be for an hour and continuous is 3 hours. But, you know, the NEC is pretty conservative, so we do that. And who knows, you may have more than, you may not charge continuously every night, but there may be that one night where you drove to Miami and back and you used up 120 miles. So you're going to charge for a little more than 3 hours to replace that. Okay, well, some of you may take a little more than 120 miles to go to Miami and back, but that's another story. In any case, the way you size your branch circuit, if you want to, let's say if you got a distribution panel and you want to see if you got enough room to put in a level 2 charger, you start out with 100% of the non-continuous load. In other words, you got your 220.87 and 220 Article 220 calculations for load calculations on a panel, and you'll come up with a non-continuous load, which might be, say, 110 amps. And you may have a 150 amp distribution panel. Maybe you got 200 amp main breaker, whatever. But you do your main load calculation, 100% at 10%, or at 10 kW at 100%. Well, we're going to do one in a minute, so we'll see what we need to do. So distribution panel bus bars are rated for 100% continuous operation. So if you had 200 amp panel, that means you could operate it with 200 amps on the bus bars continuously, because that 200 amps is not going to go down the entire bus bar to the bottom. The first 2 breakers on top are going to pick off whatever they're going to take, and they're usually the bigger ones. So by the time you get partway down, the number of amps on that 200 amp bus bar is going to be down below 100. So not nearly as much heating. It's all right at the top where the utility comes in. Unless you got some solar coming in at the bottom, then it reduces the load at the top. That's another story. In any case, the feeders to the distribution panel must be rated per 625.41. All right, not the main circuit breaker, not the bus bars, but the feeder wire. All right, and let's go back then to the 625.41. 125% of the equipment rating. All right, so you got a, let's say you got one of those 40 amp chargers, and then you have to take 125% of that, that's 50 amps. So once you do your calculation of your non-continuous load, and say you came up with 115 amps, or 110, or whatever, and then you take the 40 amps from that 50 amp circuit breaker, and you have to take that 50 amps, in fact, from that 40 amp charger, and add that to the 110, that gives you 160. And all of a sudden, your 150 amp service isn't good enough anymore. You ought to either bump it up to 175, or maybe a different service change. Except what if you've got a 150 amp breaker, but a 200 amp bus bar? That's another story. You got a 200 amp bus bar, and if you got a 200 amp feeder, which would be 3/0 copper, then you can have that 150 amp breaker and you can bump it up to 175, and then you're okay. You don't have to do a service change. You just change out the main breaker. So you have to be very attentive to exactly what's in that box. Okay, so 625.43. If the equipment itself is rated at more than 60 amps, and more than 150 volts to ground. Now that 150 to ground more than is an interesting statement, because keep in mind with the 12240 or even a 12208, the highest voltage to ground for either leg is 120. The 240 volts is from line to line, but each line is individually is 120 volts to ground. So it has to be more than 150 for this to apply. But if that's the case, then you need a lockable disconnect. And so just it may come up, not very common. 62544, all right, and again, here's the one that's interesting, 62548. This is where the code anticipates that interactive systems means that your charger is going to interact with the utility, and it can send power back to the utility if requested. And if that's the case, then you have to refer to UL 1702 and, no, I'm sorry, NEC 702 and 705. And 705 is the interconnection of a renewable power source to utility. And it says you have to have good sine waves, have to properly synchronize. It's the UL 1741 thing. And so any system like that that has a UL 1741 rating means it is capable of selling back to the grid as well as to purchasing from the grid. Oh, I've been looking at it. It's okay, nothing there. All right, so watch that 62548. We're going to see some action on that in the next couple of years. And of course, if you're in the garage, the outlet has to be more than 18 inches above the floor, not because of the electric vehicle, but in case you got a gasoline vehicle parked alongside of it, all that heavy gasoline vapor settles to the floor, and you have to have the electrical, it's more than 18 inches above the floor. And not much of that electricity, and those electrons don't stay close to the floor. They pretty much stay in the batteries. Okay, a little more 625, and then we'll move along. 52, new part 4 about wireless power transfer, which isn't really here yet. And 626, if there's going to be electric trucks. And then Ford's got some pretty nice electric trucks out there now. I've seen one that one of my good friends has, and he loves the thing. I think it's a F150. Maybe it's bigger than the F150. I'm not sure. 22087, that's important. And why is that important? Because it says that you can actually measure what your maximum use of your service is. So if you do the calculation, and it shows that your calculated demand or service demand is going to be 125 amps. It could be that if you were to measure it for a year, you could find out that, my goodness, I've never been anywhere near 125 amps. I never go over 80. So if that's the case, you can use 125% of that number instead of the number you get from the previous 220.86 is it calculation. But you need a year's worth of demand data, and most houses are not on general service demand, but guess what? Most commercial buildings are. So all you need is a copy of their last 12 months of electric bills, and take the highest demand, multiply it by 125%, and that's your new demand on that panel. Forget about what you calculated in terms of the first 10,000 watts at 100% and the remainder at 40%. You can do that. And what a surprise that sometimes turns out to be. I've done one condo that had an 1,200 amp service, and their largest demand over the year was 300 amps. That's 900 amps left over for charging electric vehicles. Well, not really. 80% of that 900 amps is available if you look at the 125% rule. All right, so these are the rules, and this 220.87 along with 625.41 is what it's all about. So keep those two in mind, and let's do some calculations. Let's say you just have a single family house. You got well, here's, if we use this example of 220.83 load calculations, 1,500 square foot dwelling with no new air conditioning or heat, just a new charger. it's going to look something like this. You got your general lighting, 3 volt amps per square feet, 1,500 square feet, 4,500. If you add up your washer, your dryer, refrigerator, 4 appliance circuits, gives you another 13,900 volt amps. Throw in your electric water heater, your electric range, another 16,500, you're up to 34,900. Take your first 8 kVA at 100%, and this because we're going to add to this thing, so then we can use this calculation. First 8 kVA at 100%, there's 8,000, and then subtract that 8 kVA from 34.9 and take 40% of the result of that, and you get 10,760. And then you throw in your 10 kW of heat at 65%, at 6,500. And then the next thing you add is your 7,680 volt amp EV charger at 125%. That's 9,600 volt amps. And see, we're just adding that right in with the 10 kW heat at 65%. We're doing the charger at 125%. And this is after we've done everything else in at the 100% for the first 8 kVA and the remainder at 40%. And that's all the stuff up here, the refrigerator, appliance circuits, water heater, range, computer, pool pump, whatever it is. You do your calculation and see what you got. So you get your total feeder load, 34,860. That turns out to be 145 amps. So terrific. If you've got 150 amp service at least, then you can put this 7680 VA EV charger in. And 7680, how many amps is that? Well, 7680 VA is essentially 7680 amps, or volt amps, I mean, or watts. That's 7.68 kilowatts times 3.5 miles per kilowatt hour. So you get about 27 miles per gallon of charging. There were 27 miles per hour of charging with this setup with a level 2 charger in a residence with 150 amp service, as long as they don't have too many other fancy things. And one of the things that's really going to mess it up is if you got a tankless water heater at 12,500 watts or something, that may push you up to needing to upgrade the service. Good possibility. But otherwise, as long as there's room for a 2-pole 40 amp circuit breaker, fine. Otherwise, you may need to do a tap, maybe a line size tap or some other way of tying it in, or splitting and putting another sub panel, whatever you have to do to add that. But the people who do electrical calculations for buildings know all about this stuff. So here's your answer to the question. The alternate service, oops, here's Q&A. Let's take a look. Sorry to miss it. Most AMI systems will give adequate residential demand data. Yeah. Good point. So if you've got an AMI system, and so whoever has that can get that information. Michael, I bet you are doing EVs. I wouldn't be at all surprised. It'd be interesting to, you want to just type a little note in the Q&As. It's interesting because for me, I can learn as much from these webinars as I can teach in some cases. So we get some really bright folks who know the material well, and I would like you all to encourage you to share that knowledge that you have. In fact, even what is an AMI system? I have to admit, I'm not sure what that is. I'd have to think about it for a while, but I'm going to move on, and maybe Michael, maybe you'll type in what the AMI stands for. Is the first 8 kVA load for 1 charger or 2 chargers? Doesn't make any difference. It's for your existing load. The charger is not added in until you've already taken in this 8 kVA stuff. So there is no derating on the charger. There's no 40% factor. There's no anything like that. If you have 2 EVs, you can have an allowance for 2 EV chargers, but you don't need to, because you've already seen what a level 2 charger will do. It will charge at 27 miles an hour, the one we just did. And if you drive 50 miles in a day, that's going to take less than 2 hours to fill it up. You can have another charger outlet that talks to the one next to it if you got 2-car garage, and then you can plug in both cars at the same time, and they will simply share the electricity. And that's allowed because as long as you're doing load limiting, the NEC provides for that because they know that the chargers can talk to each other and limit the load from the service itself. So it's not a big issue. This open charge point protocol is lets the two vehicles just be charged separately or more slowly at the same time. You can tell it how you want it to do it, and they will. You just give it the rules, and they follow the rules. So let's see. Click, 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 click. Okay, and if Mike will share what that is, here's the Q&I came up. AMI, Advanced Metering Infrastructure. Okay, yeah, and that's exactly what we're talking about. Because advanced metering means that it's going to be time of use essentially, and it's also going to be load limiting and do some fancy stuff. There are distribution panels out there now that will have you can program them such that the panel itself will have contactors on every circuit breaker, such that it can shut down that circuit according to, call it the advanced metering infrastructure, because what you're basically doing is watching the total current either flowing in or flowing out from that structure and limiting it to whatever the program says you need to limit to. So yeah, this is the fancy stuff that we're getting into, and that is going to be so much fun. I wish I weren't 80 years old. I mean, I'm happy that I made it this far. But if I were 40 years old, my goodness, this stuff would be going crazy. I probably wouldn't sleep at night because it would just keep me awake thinking about what are they going to think about next. And I do appreciate, very good questions and comments you all are coming up with. Here's an alternative service. Here's your 22087, okay? And it says you can do that, but it doesn't happen very often. So you can also measure for a month if you know this is a month when you have your your highest bill. And if you put recording ammeters on L1 and L2 and measure both currents for a month, then you take the larger one and multiply by 125%, and that's your new load calculation if you want to wait a month to get it, and if you got the recording ammeter. So that's what you can do at 22887 in a residential situation. But like I said, if you got a general service demand, then you just look at the electric bills and take the highest one of the year and figure out how many amps that is. We're going to come to that. So in any case, 125% of that measured load added to what you got with 220.83. If it's smaller, use it. It's okay. So maybe that can save you the problem of having to, say, go higher than a 200 amp service, or maybe you can set your charger to a higher charging rate. And by the way, most chargers are adjustable. So you buy one charger and you can tell it what rate you want to charge it at. We're going to plug it into a 30 amp, 40 amp, 50 amp, 60 amp, 70 amp, 100 amp circuit. And that means 100 amp circuit breaker, and it will decide inside. And there's interesting things about changing that. And of course, you change that, the price you pay is to pop your main breaker. You don't want to do that, so you want to make sure you set your demand of your system to something that's going to maintain the integrity of your circuit. And of course, the AMI, that's going to do it for you. So anything of kVA less than 25.26, if you use 220.87, then you'll use the 220.87 calculation. What about three-phase? That's the fun part. Let's see, how are we doing on time? 45 minutes, all right. What about three-phase services? Because single phase is a piece of cake. Three-phase, little more complicated. Let's say we got a 200 amp, 120, 208, three-phase service, and we want to connect 16 amp, in other words, 1920 watt single phase level 1 chargers. So that means we're going to go line to neutral on these. And we want to know how many we can connect. Well, first of all, they're single phase, so they're line to neutral. And the loads will be continuous, so we have to take the individual at 125%. So that means 16 at 125% means you're using number 12 wire or bigger, and a 20 amp but single pole breaker. Okay, and each charger has to be on its own branch circuit with a single pole 20 amp overcurrent protection if we don't have any communication amongst the chargers. All right, so let's assume we do that. Nothing fancy, just every charger has its own circuit. And there is no diversification factor in the NEC for multiple chargers, but the NEC does allow you to do load limiting and measuring the AMI stuff, so that you can have multiple chargers on a single circuit. They simply have to talk to each other. Let's say we got 200 amp feeders. That means the maximum load on the bus bar has to be below 160 amps, 160 or less. So let's say we got a balanced three-phase system. That means the power being delivered is 1.732 square root of 3 times the line-to-line voltage times the line current. And if it's balanced, then the line currents are going to be the same. So this then tells us the total power available, 1.732 times the 208 volts line-to-line times 160, 57.64 kilowatts available for charging. And we're going to divide that amongst these 1.92 kilowatt chargers. So 57.64 divided by 1.92, or 57,640 divided by 1920 if we're all watts. That says we can have 30 chargers plugged in to this without any kind of diversification at all. It's just a three-phase 120 208 service with level 1 chargers, and that'll run 30 circuits. The 30 chargers. And if each of those circuits can have more than one charger on it because the chargers talk to each other, then maybe we're up to 90 or 100, something like that. And this is realistic in a place like a condominium, to use a single three-phase 200 amp service to service and charge up a whole lot of vehicles. And the nice thing about 30 is that's 10 chargers per phase, nice balanced load. So you can't beat that. So how do you know what the line currents are for 30 chargers? Well, the fun of that is that, let's say you got a 200 amp 30 position panel, because that's going to handle 30, 20 amp, one pole circuit breakers. And we put 10 chargers on a phase. All right, load calculation, phase currents says we got 16 amps on each of 10 circuits. That's 160 amps, no neutral current. So that's what we're supposed to have, 160 amps per phase. And now, if we distribute it just like this on a panel, phase A gets the first one, B, C, I only had room for 12 of them here, but notice we got 23,040 for 12 with 64 amps per phase balanced. And if we then extend that off to 30, with 30 of them, we're going to get 57,600. And that's exactly what we calculated on the last slide as how much power is available. So it would seem like this is all we have to do. It's just list phase to phase or phase to neutral. Well, it works fine for phase to neutral, but there's a little surprise on phase to phase, and that's what I want you to see. And of course, the alternative method is how many can you connect to 120? You can just draw a circuit here and show that you connect. You got line 1, 2, and 3, and neutral current. And the neutral is the sum of the 3 line currents. If you notice, the neutral current's going back to the neutral point, and the line currents are all coming out. And of course, these are out of phase, so they can sum up to whatever. So let's see what they're adding up to. Here's charge controller number 1, and it gives some current in line 1 and some current in the neutral, but nothing in line 2 or line 3. And that's going to look like this, line 1 current. And now we add another charge controller here, and we got charge controller current. So now we got charge controller 1, charge controller current, both coming into the neutral. And so the neutral, there's your line 2 current. And the sum of those two gives you the neutral current. And you have to add them point to point, or vectorial, or phasors, or whatever you want to call them. And you see the neutral current is equal to the line current when you've got an unbalanced load. We add our third charger and the third neutral, then the neutral current goes to 0. And we have a nice balanced system where the sum of the neutral currents is 0, the sum of the line currents is equal to the sum of the charger currents connected. And that's why it worked out so nicely in that last example. Question, let's see, what do we got? EV chargers consider nonlinear loads such that we need to consider harmonic concurrence. Nobody has ever said that the EV chargers have a problem with harmonics. They do not have chopped up waveforms necessarily. The question is, what happens when they try to balance the loads and cut back on the amount of power? And that's a good question. I have never heard anybody anywhere, even in the National Electrical Code, say that we need to take into account third harmonic component that would come as a result of nonlinear. And so I am not aware. Brad, if you got good information on that, we want to hear about it, because nowhere that I've ever read anything has anybody mentioned, make sure you allow a certain amount for third harmonics. Now, third harmonic, normally what that's going to do is give you some neutral current, but not necessarily going to change your line current. So, and it's the line current that's going to trip the breaker. And the neutral is not going to be a reduced size anyway on this. It's going to be full size. So given that third harmonic, what it does is when the 3 add up in the neutral, then you have something different from 0. But it never exceeds the value of any of the single line currents. So I guess even if there is a little bit of third harmonic, it's not going to be an issue. Okay, let's see. Again, excellent question. I appreciate that. So this is basically what happens. And so the neutral never exceeds the largest line current, even if there's some third harmonic on it. It's not going to get bigger. 3-phase load calculation for 40 amp 208 volt chargers. Let's do it. Very exciting. You might try it like this. Here's one you're going to connect across phase A and B. Another one goes to B and C. Next one is C to A. And on, just like that. And sure enough, you add them up, 160 amps per phase, 49,920 volt amperes. Why? Because each one is 8320, and you add 6 of them, that's 49,920. So, except for one little thing, for a balanced 3-phase load, and this is certainly a balanced 3-phase load, line to line, the volt amps is 1.732 times line current times line voltage to 57,641. And we only got 49,920. What happened to the extra 8,000 watts or so, or 8,000 volt amperes? Wow. Now that's an interesting thing, by the way. This says volt amperes, not watts. And because there's a fair amount of, I think there's an isolation transformer in most of the chargers to make sure that there's an ungrounded supply going in to the car, except for the neutral. This is one of those things I'm not absolutely sure about, but it doesn't affect the calculation here in any case. So there's a problem. Let's take a look at some diagrams, and maybe we can figure out why we get 49,920 instead of 57,641. I bet we can. And I bet if we couldn't, I bet I wouldn't have had this slide here. Let's see, we got a Q&A. They're considered highly nonlinear and is a concern if multiple units operate at the same time. Okay, Michael, that's good. Then we need to learn more, but presumably, once again, the measurement, you had a plan reviewer in Seattle consider these nonlinear loads, and that we had to re-rate conductors for NEC 310, 15, C1, 4 more current conductors and 1 conduit. Oh, that's interesting. Very interesting. Yeah. All right. That would say the neutral current is significant then, because normally the neutral current is simply the difference between all the other currents in the lines. I need to look into this, Brad. This is excellent. First I've heard of that. First data. I need to find out exactly what goes on here. So in terms of and of course, the local jurisdiction is always the final word on this. And this is assuming that the neutral currents are not going to be a problem, but certainly, yeah, that's going to give you, and of course, you have to have all 4 conductors in the same conduit, unless you're running parallel conductors. So that would be a D rate. All right, but presumably that means that the neutral current is comparable to the line currents. And presumably, if that's really the case, then you may have to, maybe you don't have to derate the conductors. Maybe you just have to reset the chargers so that they charge at a different, the next lower charging rate. So okay, I'm sure this is going to get a lot of attention, because if this is really true that it's happening in a local jurisdiction, then that's definitely going to get attention. And this is one of those things that the ever-changing world, by next year, people will have more data, and we may see changes in the 2026 National Electrical Code. But there is nothing, well, there is something in the code that says if you have a well-defined third harmonic, but there's nothing in 625 that talks about harmonics that I'm aware of. And if somebody's aware that NEC 625 has some information on harmonics, that would be good to know where that is. And I looked at 625 pretty carefully, and I could have missed it. If I did, I need to know where it is, and I would appreciate it if you would share that information as well. Yeah, this is very interesting about Seattle. It almost sounds like us with PV plants in Miami or certain places. They really rake you over the coals. I wonder if anybody has any actual measurements to show exactly what's in these conductors. I'd love to get down to someplace that had a bunch of that's the trouble with being old and confined to not getting your hands in the equipment as much. But I'm going to find somebody who can get access to one of these and clamp an ammeter on the neutral and see what's going on. This is something we need to know about, and hopefully somebody's got some valid information on the internet. That's always fun to find as well. So again, thank you very much. Good comments. Good comments. For the moment, this calculation procedure would be valid until somebody finds something in the NEC that says, or something that says in the installation manual of the charger. And that's where this information ultimately ought to be. And if the charger installation manual says you got to do this, or you got to do that, you got to take care of third harmonic distortion on the neutral, then you got to do that. The bottom line really is all this calculation is well and good, but if there's something in the manufacturer's specification that says that you got to modify it, then you got to follow the manufacturer's rules. But still, the whole basic concept here is that it doesn't take nearly as long to charge a car as you think it does. And fact of the matter is, with 3-phase, the number of volt amperes is different, and we need to figure out what's going on here. So let's figure that out. Why are they different? Well, if we do it a different way, let's say we have sets of 208 volt chargers. Let's start connecting some up and see what we get. And then let's connect them and then see what the current is. Here's the first one, 40 amp charger gives you 40 amps, and then it's between A and C. So therefore we can argue that A and C both have 40 amps, and we're not paying attention to phase. Obviously they can't both come out, one has to go in, but we're talking AC. And the point is the line currents, if you just measure it with a clamp-on ammeter, they're both going to read 40 amps. All right. And then we connect another one. And now we got 40 amps coming out of A that feeds charge controller 1, and another 40 amps from A that feeds charge controller 2, and 40 plus 40. Wait a minute. 40 times 1.732, why not 40 plus 40? Why not 80? Anybody know the answer to that? And of course, the answer is that just as these drawings are 120 degrees out of phase, so are the currents. So in this case, 40 plus 40 equals 69.3. And if you got your handy clamp-on ammeter, you can measure the current. And you know, if you want to go into phasor analysis and fancy math, you can prove it. But this 1.732 is the difference in the currents between these two lines. So we got 40 amps in line C, 40 amps in line B, and 69.3 in line A. A little unbalanced, but it's not 80, it's 69.3. So now let's put in a third one. Now we got 40 amps for charge controller 3, 40 for charge controller 1, 40 for charge controller 2. And so what effect does that have? We now have two of these charge controllers connected to each of the three lines. So each of the three lines now is going to have 69.3 amps rather than 80. And again, you can prove this by your clamp-on ammeter. And here we're looking at line currents. There is no neutral. These are line to line. Okay, so that's another important consideration. Q&A, what do we got? Nothing in 625, but will be elsewhere, like Brad has noted. Okay, maybe so, but one would think since 625 is specifically designated to electric vehicles, one would really expect it to show up there. And if somebody can find it someplace else, I mean, we know that there's the third harmonic statement in 310.16, I think it is. And or maybe it's just in 310. There is a statement that says if you've got third harmonic on a neutral, then you can't downsize the neutral. It has to be sized the same size as the other conductors. And they probably then would have to say that, all right, you got 4 current carrying conductors, and if they're all carrying the maximum current, then you're going to have to derate. So we do know that is in the chapter 3 and all the tables 310.16 and so forth. And but I need to see that in 625 because I think it's really important. If anybody here knows anybody who's on the NEC code panel, that really needs to show up in 625 because that 625.41, it tells how to calculate the now that another interesting thing is that extra 125%. There are a lot of things you can do if somebody does prove there's that third harmonic there, including some filtering. And that is another way to get rid of third harmonic, although that's a little lossy. And you got to be a little careful with that. It's third harmonic is only 180 hertz, so not you have a pretty sharp cutoff filter to be able to deal with that. Well, okay, so appreciate the comment anyway. So at least I didn't miss it when I was looking through 625. Okay, thank you again. We had a well-educated group out here today. It feels good. 336. Just want to check here. So here's the secret. It's you got to multiply this by 1.732, not by 2. So if we add 3 more chargers to the system, then the load is still balanced, okay? But the individual chargers are still 40 amps, or in other words, you've got 80 amps between line 1 and line 2, or phase A and phase B, and 80 amps B to C, and 80 amps C to A. But when you convert that to line currents, it's going to be 80 times the square root of 3. As we'll see. Here's your 80 amps, here's your 80 amps, 138.6, another 80. All 3 lines now are balanced. So we now have 6 chargers at 40 amps each, and we've got 138.6 amps. Okay. And this is what we had before, 6 chargers. And let's just check it out here. The kVA for the total load, 40 times 208 times 6 is 49,920 volt amps. Okay. Yeah, 40 amps, that's 208 volts. Okay. And we've got 6 of them. So that's 49,920 actual volt amps consumed by the charge controllers. And the valence load calculation says it's 138.6 amps. That's the line current times 208 volts times 1.732. Voila, 49,920 balances out. So the square root of 3 thing comes into play here. And these are line-to-line connections with no neutral anyway. So in this case, you're only going to have 3 wires and a ground wire going through that conduit, and there should be no penalty for 4 wires because there's not supposed to be a neutral anyway, with 208 volt chargers. On the other hand, if you have unbalanced 120, or if you have 120 volt chargers that have a lot of third harmonic, then you're going to have some neutral current. So the whole idea is to stay away from the 120s, and then you don't have a neutral to worry about anyway. You got 3 wires, currents 138.6, and no derate. So that's one solution to the problem. Pretty clear. I mean, NEC says up to 3 wires in a conduit, this is what their ampacity is, and nobody argues with that. The only argument there is whether your contacts are 90 degree or 75 degree, and whether you're using THWN2 at 90 degrees and have to derate to 75 degrees and all that stuff. That's another story. But the third harmonic stuff is out of the question here with the delta connection. So interesting. So we're good. 138.6, not 160. But if we try to add 3 more, we're going to go over 160, and we can't do that. So bottom line, the line current is the total power being delivered divided by 1.32 times 732 times line voltage, if you've got a balanced collection of chargers. And if they're unbalanced, you can still do a good conservative estimate by saying, if I've got 4, I'll simply consider the line currents to be what they would be with 6. And if I've got 7, then I'm going to have to use 9. And then that still gives you a reasonable, that means your calculation of the line currents are going to be conservative if you do that. So if you have 7, you might as well put 2 more in because it doesn't change it. Okay. So there's the story there. And of course, the power, if you have a power factor involved, and we weren't, I mean, they call them volt amps, so that implies a power factor. But the power factor doesn't imply that we have harmonics or non-sine waves. That just says the current and the voltage are out of phase. But still, the line current, you're going to get this data, and you're basing your calculation on the line current anyway, which is going to be in your data in your installation manual for the charger. So, charger currents, loads balanced. This is the bottom line of what we just did. So if we went up to 9 chargers, we have 166.3 amps. That's 6.3 amps too much. So what if we reduce the charging current by 1.21 amps? Then you could use 9 chargers. Or just go down to the next lower level if you want to use 9 chargers and you've got the load management capability in the system, then don't charge at 40 amps. Charge at 30. And then you put more chargers in. And then if you also have the chargers talking to each other, and then you just sell for a little less than 27 miles per kilowatt hour, or 27 miles per hour of charging. So condominium, if we use these rules, okay, and we're going to do the example. We've got an area served by this is actually my building. We have a service of 800 amps of interruptible service, another 800 of uninterruptible. So we're just going to tie into the 800 building load and forget about the individual dwelling load and see what we can do with that. Okay. So you get your 12 months of less electric bill, so you can use 220.87 to see what your demand is. Then we add the chargers until we're up to the most what we can use. So what happens? Let's do it. Got 120, 208 3-phase. The individual units are 120, 208. Here's building's electric bill, and look what we got. General service demand, hot dog. Kilowatt hours used, demand kW. 84 kW demand, 58,920 kilowatt hours. It's the 84 kilowatt demand that we're interested in. And this happens to be the highest bill of the year, the highest demand. So what is 84 kilowatt hours to a 120, 208 service? They're kilowatts, not kilowatt hours. So there's your demand charge right there, along with the energy charge. Multiply that by 1.25 because that's what NEC says you have to do. So instead of 84 kilowatts, we got 105 that the building is at. And because that's you have to take when you're doing the actual measurement or from the meter, you have to do 125% of that to be conservative enough. And so we got 105, and then we divide that by the 1.732 times the line-to-line voltage, and we get 291 amps. So that means we're 291 out of the 800 amps are committed to the building, but that leaves 509 amps back left over as available for EV charging. And of course, that's not all available either. We can only use 80% of that. So with 80% of that, we got 407 amps available. And here we were talking about 200 amp services being enough for 50 or so vehicles. So, you know, wow. And that was at sharing circuits so that maybe charging one at a time for 2 hours a day and having 10 or so on a circuit. Wow, there's some interesting stuff we can do. Level 1, we know what we can do with that if we keep the load balanced. We can put 25 per phase or 75 of those in there. And then we talk about whether we have to do the funny stuff with the 120 type volt charging. Or we can say, now we're going to go with level 2. So let's see what we can do with that. So if we take those 407 amps and divide by 15.65, monitor line current and stuff, then we could put 26 chargers per phase. But let's take a look at what else we might be able to do. Here's a Q&A. Let's see what we got. Won't you also need to apply a power factor to the existing load since you are getting kW as demand from power company? You know, that's interesting because NEC says you can use kWs. And yeah, that's a good point. But that's where the 125% comes in pretty handy. Because if you're taking as your load 125% of the kW demand, then that gets you down to a power factor as low as 0.8, and it's probably not that low. So I guess it is kind of taken into account with the 125% number. Maybe that's why they put it there. I never asked him. That could be. Good question. Again, I've never had so many good questions in one of these sessions. I appreciate it. It's great. Makes me excited. Okay, so let's see what we can do. Oh, another question here. Oh, I know what I didn't do. I didn't do the done. Okay. We can do the 16 amp level 1, but let's move on and see what we can do with level 2s. And if we do a 40 amp unit, multiples of 3 like we just did, we know we got 69.3 for 3 of them. We know if we have 407 amps available and we use 3 of them at 69.3, that's a factor of 5.873. So we should be able to do at least 5 rounds of 3. Okay. And so that would be 15 chargers. All right. 5 on each phase for that 407. And we can do that experiment. 5 times 69.3 is 346.5. It's less than 407. We expected it would be, but we can't go more than 5 or we'll be higher. So, because we're going to have that 1.732 factor in. So that's less than 407, but we can use that remainder for lower power chargers or whatever else. But let's see what we can get with just 15 chargers. I mean, this 15 chargers, what's the possibility here? We got 60.5 amps per phase still available for smaller chargers, but a 40 amp charger charges at 30 miles an hour. And so over 1 year of charging for 1 hour a day, you're getting 10,950 miles. If you use it for 10 hours at night, that's 109,500 miles of charging in one night for 1 hour of charging with one of these things. And if you got a bunch of these, this is just a single 40 amp charger over a year's time would give you 109,500 miles. Imagine if you have 15 of these. I mean, that's a lot of miles, okay? If you got 15 chargers operating 10 hours a day, that gives you 4,500 miles of charging in one day. And if they're operating for 24 hours a day, you get 10,800 miles in a single day worth of charging from these 15 chargers. Okay, and that 10,800 can go to however many vehicles you want to. But these numbers are really something to think about because, and even if some compensation for harmonics or whatever else gets thrown in there one way or another, that's going to be compensated again. And we're not going to lose more than 10% of this. And so we're looking at charging over 10,000 miles a day if we do full 24 hours worth. Probably won't because that gets into demand issues. So probably be less than that. But just to get an idea of how much is available. And so what if we only get 8,000 miles a day for a group of 15 chargers, which might be 30 or 45 cars? How many 45 cars are going to drive a total of 10,800 miles a day? Not very many. What do we got here? 125% heating adjustment. Yeah, that's correct. Power factor is probably covered by the extremely conservative NEC calculations. Yeah, I suspect so because I agree that 125 is build up the heat, and that's why it's 80% for 4 to 6 and down to 70% for 7 to 9 and 50% for 10 and more. So, of course, the trick here then is don't put them in a conduit. Of course, kind of hard to get by doing that. You could do that if you had a properly designed racking for the wires and the proper insulation and stuff, but I doubt anybody's going to do that. But a good point. It's heating because that's your conduit fill adjustment. You got to get rid of that, and that's why you have the thing about the 90-degree terminals and 75-degree terminals. So it's a heating issue, and you don't want it to get too hot. So in any case, when people say that for 45 or 40 unit condominium, you need to have 40 different chargers, each of one is rated separately at 50 amps or 40 amps or whatever. Now that's probably true for a motel where people are going to try to dump in 200 miles a night. But how many condos occupied by people about 100 years old and older are going to be driving 10,800 miles a day for 15 cars? Interesting questions. So these are just some numbers you should know about, so that when people start arguing, at least you'll be able to explain some of this stuff. The point here, obviously, is you need communication among the chargers, and any decently designed system is going to make sure that the chargers, I mean, there's some of these systems out there, the commercial can have a single controller for 20 chargers, and that's probably going to change. It probably has changed since the last time I looked. So if you got that many on a single circuit, 20 chargers on one circuit for a day, and it could very well be adequate. We'll see. What do we got? Another question. Equipment panels, breakers, not normally designed to carry 100% continuously because they can't get the heat out of the enclosure. The rating is done outside of the enclosure. Some panels can be 100% rated. Yeah, well, that's fine. But the thing is, you also have to talk about the feeders to the panel, because typically on a 200 amp panel, you'd have 2-aught copper. And if you really want to get this 160 amps, you're going to need 3-aught copper to get the 160 out of it, or actually, yeah, you're going to need 3-aught. So you need to be careful with those. Our chargers typically controlled wirelessly or through low voltage cables. My understanding is that these are power line carrier type communication, but can be wireless. I know that the communication that my vehicle has when it's plugged in is wireless and goes by way of cell phone. So I think both happen, because when you've got a single circuit that has a single controller for more than one, then it is probably power line carrier. And some of the problems with wireless is that it's got distance limits, and it doesn't like to go through certain walls that have a lot of reinforcement bars and things. But honestly, I don't know. The whole word here again, the key word is typical. And there's some of each, because you can see the antennas on some of the controllers. And so clearly, so I don't know which is more commonly used. And that's just like on a photovoltaic system. There's some of each used, and it's all, the individual system is what determines that. Again, you got to read the specs. Now, let's see what else we got here. Yeah, right. Okay, we got that. Okay, and what's our time here? What's we looking at? 3:54. All right, we're getting close, doing too reasonably well here. And like I say, there's some extra stuff, I think, at the end that we may not get to, but it'll be on the slides for when you. All right, so anyway, there's an awful lot of charging you can do with the level of 40 amp charger. You can get an awful lot of mileage out of that. Or let's just say out of a 200 amp panel, limiting your line currents to 160 amps. Okay, let's see what else we got here. What if you mix them up? Well, yeah, you can mix them up, and I'm just going to show the numbers here. Because those leftovers that you didn't use on level 2, you could use on level 1. But who knows, some other magic gadget might come out you want to use that electricity for another day anyway. So we've already shown how we can take care of all the vehicles there. But if we're going out, if we get outside of, if you just try to connect to dwelling services, there can be a problem on that, and that's because of the derating factors. If you do the regular calculation for 1 unit and then you got 25 units, you're going to have a derating down to about 30%. And it's that total load on the distribution system of meters. If you got a 25 meter bank, it's the total load on those 25 meters that you have to add your one additional charger to. And it's very easy to go over by connecting them to the individual dwelling services. So I'm just going to tell you that be really careful and do that calculation very carefully, because you're going to have to add not just to the one unit, but that one unit is connected to a bunch of meters, and it's probably got a single service. Like my building has 21 units on one 1200 amp service and 22 units on another 1200 amp service. And when you do the calculations on that, there's not much extra room for 125% of a level 2 charger on top of that. So watch that one really carefully. And the math is here. You can take a look at it if you're interested in it. Couple more questions. What do we got? Not all condo residents have EV cars. Absolutely not. Who pays? It all is up to the condo. Condo next door, they tried to set up an LLC that would sell electricity, and then they got into all kinds of issues about what about with this, that, and other place. So part of this also is governed by law. And in Florida, it is allowed to have third parties selling electricity for EV charging. So it is allowable for a condo to plug in EV cars and monitor the number of kilowatt hours they're using, and even the kilowatts if they want to, and establish a rate to bill people, and they can get it by way of the communication system. So there's a lot of flexibility here, and most people don't realize that. So like you say, what about the common space where wires go? I mean, my building is wired a bunch of little circuits for people who are gone for 6 months out of the year that want to plug in trickle chargers. And since these trickle chargers use almost nothing, if one EV charger gets plugged into each trickle charger circuit, we're still good. But who pays? That's up to the condo to decide how that works. And you can actually get the billing information off the chargers themselves, because they'll tell you the number of kilowatt hours they've used. So let's see, talking about loads for EV chargers and condo services. Are you talking about individual? Let's see, connected directly to each condo load center. 220 for overall building service load. Yeah, see, that's 63 condos with the 23%. When you do the individual condo loads and then take the 23%, it's probably going to come pretty close. This would probably have something in a really big service. 63 would have probably almost 3,000 amps of service. But if you try to add to that, you can't add very much, because the diversified load at 23% gets you pretty close. And it may not be 30, whatever the number is. So you still have to add, and you're designing the building. Yeah, I mean, my recommendation on that is work it out so it comes. Either you have to put in probably larger meter banks than you otherwise would. But if you're talking about the condo service itself, then you're talking about what we've just gone through in the calculations. And at least 40 years ago, things were really over-designed. And with all the LED lighting and stuff like that, and it's much more efficient air conditioning, the building loads are significantly lower than what they were designed for 40 years ago. New one, that's another story. But if you can get the ownership, that'd be an amazingly, you can design it. You would have to show the individual units designed the way we did earlier, and then you'd apply that 23% diversity factor. I mean, that's legit, because you're including the EVs as 125% for each unit. And so you could do that, but it's probably going to bump up your individual unit service significantly. I'd love to see what the number result comes out. I'll try that sometime. So I would say try it both ways, run the calculations both ways, and then ask the owners what they would prefer. Because if your condo has got provisions, given that we're looking at 18.5 million EVs by 2030, if you're building a new condo, a level 2 EV charging station for each unit is going to be a real selling point. My prediction, of course, what do I know? But just give it some thought, and it makes sense that that's a very sensible thing to do. Because for one thing, there's so many old condos like mine where are also occupied by curmudgeons who don't want to spend a penny, that if you got a new one where it's right there, those things are going to sell like hotcakes to people with their Teslas and stuff. And what a nice thing. Their garage won't smell like fumes. They won't have any loud engines coming in and out, all those nice quiet electric motor. Anyway, that's maybe too long of an answer, but that's what I've got to offer there. And of course, not all residents have EV cars. And so generally what happens is the residents are supposed to pay for their own electricity, and we've offered to pay because we know what we're using. And they just found it's way too complicated to collect 50 cents a day from us for the electricity we use. So 50 cents, no, we don't use that much, 40 cents. So anyway, that's kind of an answer to Paul's question and William, and I appreciate those good questions. Again, every single question has been good today, and that makes me feel really good. All right, let's see. We're almost there. Let's hurry here. What do we got? Maybe we're already there. Yeah, we're presumably all over right now. I'm willing to keep going for a little while. We've had a whole lot more discussion than normally. Let's just click through here to the end, okay? No more questions. Just let's get to the end. And here's your demand factors and the single individual unit. You can run through this calc and see what it does. The interesting thing is, okay, there's more than the condominiums in the world. What else is out there? And yeah, these are things you can read fairly straightforward. Restaurants is an interesting concept. Somebody parks into a level 2 charger for an hour and a half, gets out of the parking space, somebody else plugs in for an hour and a half. So you can keep that going almost continuously while the restaurant is open, and maybe even after it's open, depending on what kind of payment schedule is there for the people. And there's a lot of credit card type things going in where you can just pay by credit card. So interesting stuff. Lodging. There, clearly people are going to charge for a whole lot more than an hour because they're going to drive more than 30 miles. And if you had a parking attendant who could move the cars every time one is filled and then put another one in, that's one way. But a whole lot easier if you just have more places to plug in and have load management instead. Motels. Here's your 7 hours of charging. Level 2, level 3. Good question where that might be. But mostly that's going to be out on the big highways. And here's just a few notes about it. Anything else worth thinking about? The service size inadequate? It could be. You may have to upgrade the service or install a new one, or simply you may need a new transformer and things like that. And system interconnections, yes, they do. And it's really interesting to look when you got solar and battery storage involved with an electric vehicle. And there's where you read your instruction book really carefully to see how you program that. Because that way you get carbon-free charging of your car. And there's lots of communication links, and Tesla has them and others do. And that's why you got to read the instruction book. And the other thing people often don't think about when they do their chargers, that you're not necessarily going to do all your charging at home. If you drive a lot, you're probably going to be doing some charging away from home. So all kinds of interesting options here. And there's 2 current monitors. There's the uniform distribution. Everybody gets the same amount, or it's first in, first served. And there will be others. And Blink is one of the players if you want to get some, and I'm not endorsing Blink. I have no stock in the company. It's just I've read some of their stuff. And you can Google them and they give you some data. And it's not not necessarily that easy to get some data on specific chargers. And Blink has quite a bit. So, and there you see, you read it all on your cell phone or on in your car. So again, I'm not pushing Blink, but I'm saying that's sort of direction we're moving. And these are the kind of chargers we're looking at now, the one way, but we're going to be into the 2-way stuff one of these days soon. I like to call this the beginning of the story because we're just getting started on this stuff. And here's some appendix if you want to do the phasor analysis of the 3-phase stuff. You can read that if you get the handouts. So I thank everyone for your attention today. I hope you got something out of it that made it worth sitting here for 2 hours. And feel free to share any of this information with friends. Feel free to get back by way of the host if you find answers to any of those unanswered questions that we had today. There were some dandies, and I'm going to be doing some looking at things. We got Q&A here. What do we got? Okay, Steve, you're very welcome. Okay, and we're going to shut down here in just a minute. So if you need anything you need to add, you can also send a question to the host and he'll forward it to me if you come up with something later, if you're going through the notes again. And we'll respond to you. Okay, we still got 53 folks there. I'm going to hang on for a while until most people have shut down. But meanwhile, I'm going to be watching what's coming up in the Q&A box. And thanks for coming. Hope you have a great season. Happy holidays. Probably everybody's going to buy a Tesla now or a hot Mustang for Christmas, because now you know you can charge it in your garage. And all the information on certifications and stuff for attendance, look in the chat box. That's all sitting there waiting for you to take advantage of it. Okay, Mr. Host, I guess it's okay that I sign out here. So I'm going to stop sharing the screen and find the exit button. And once again, anybody still listening in, thank you very much for your participation. Now I know why they call it participants. We had very good participation today, and I'm very happy to acknowledge that.